This video is about the integration of rational function by partial fraction decomposition. Having a rational function, proper rational function, R over Q, what we have to do, we have to express the function as a sum of the partial fractions. How can we do? We can factor out the denominator, Q of x, as far as possible. It can be shown that any polynomial Q of x can be factored as a product of, and then we have 4 different cases. Of course, product of linear factors, which each of them is different. None of them is repeated. That's case 1. Case 2 is linear factors that some of them are actually the same, repeated. Case 3, which I will focus on in this video, is the case that we will get quadratic factors which we can't factor out further, irreducible quadratic factors. Because we know part of the quadratic formula, b squared minus 4ac is less than 0, we do not have a real roots. That means quadratic irreducible factors, which actually none of them is the same, none of them is repeated. That's case 3. Case 4, it's similar. Also, we will end up with quadratic irreducible factors. However, some of them are repeated. But this video, we will focus on case 3. Case 3. Again, I'm just repeating the information. Q of x contains irreducible quadratic factors, none of which is repeated. And now the point is, how can we set up our potential partial fractions? We may look at this expression. Okay? We have x over x minus 1, x minus 2, x squared plus 1. We can see quadratic irreducible. We can't factor out further x squared plus 1. And also x squared plus 4. So we can definitely see that we will end up with only 3 partial fractions for this expression. Even if the degree of the denominator, degree of the polynomial from the denominator is 5, 2, 2, and 1, since both of these are quadratic irreducible, we will end up having this as a partial fraction, simple fraction. Okay, and we remember from the case 1 and case 2, we will put a, the constant a. However, now on the above the quadratic one, we cannot just put the constants like b, c. We have to put the expression which is actually the linear expression, the whole expression, like mx plus b. Let's keep the alphabet in order. I will put bx plus c, dx plus e. Okay? And this is just the way to set up the partial fraction. One way that I can maybe explain this, since this is quadratic, we have to have on the top the polynomial which is just 1 degree less. Okay? Like even thinking about this one is the linear factors. I can say is x taken to the power of 1, and I can pretend that, this is also a polynomial 1 degree less, which is x to the power of 0. Of course, x is not 0, then we have 1. No? That means that's the way. That means please remember, when setting the partial fraction, for the case 3, the irreducible quadratic factors, we have to put the entire like expression bx plus c, dx plus e, mx plus b, any form, of course, any letter is allowed, but we have to have a linear factors. Okay, I will remove that one because it looks like a square. Okay, that means let's take an example and let's integrate. Example number 1. Integrate integral of 2x squared minus x plus 4 over x cubed plus 4x dx. Definitely this is the proper rational function because the degree in the denominator is unique. Great. Now let's try to factor out denominator, because that's always the point. We can factor out x, and then we have x squared plus 4. Of course, x squared plus 4 is irreducible. That means we're expecting two partial fractions, dx. X and then x squared plus 4. Above the x, we can put just a constant. But above the quadratic factor, we have to put the linear form, bx plus c. Okay, let's find a, b, and c. We will copy numerator 2x squared minus x plus 4, and I will create a new numerator using the sum of the partial fraction. If I will combine this and create again the common denominator, which will match to this one, I have to multiply the quantity a by x squared plus 4. This allows me to have the common denominator for the first fraction, and having a common denominator for the second fraction, I'm missing x. That means bx plus c must be multiplied by x. Bx plus c will be multiplied by x. Okay, and now let's try to substitute maybe 0 for x. Substituting 0 to the above equation, I will have 0 minus 0 plus 4, 4. And then 0 plus 4 will be 4a, and this is 0. That means a is 1. Great. And now we can see we do not have more zeros of the denominator. That means I will pick a random number, the easiest number, x. 1. X equals to 1. And let's substitute. 2 minus 1 plus 4, I can write this down. 1 squared plus 4 is 5a, and 1 times b times 1b will be b plus c. And then we have 1, we have actually 5. A is 1, that means I can substitute 1 times 5, and then b plus c. And if I will switch the side, b plus c actually is 0. It's okay, because we know that this x equals to 1 wasn't the 0. That means I end up with the two unknowns. Let's create another equation. Let's substitute -1. Okay, -1 squared is +1. That means we will have 2 plus 1 plus 4. -1 squared is again 1 plus 4 is 5a. Negative times negative b will be positive b, and -1 times c will give me -c. Okay, this one is 7 plus 5 times 1, because a is 1, and b minus c. B minus c equals to 2. Okay, that means I do have a system of two equations. B plus c equals to 0, b minus c equals to 2. Of course, any form of solving the system of two equations is good. We can actually add them together. B plus b will be 2b. C plus -c, of course, is 0, 2. B is 1. Oh, really nice number. If b is 1, we can see that c has to be opposite -1. Okay. That's, we do have the coefficients. Let's finish the integration. 1 over x plus 1x minus 1 over x squared plus 4. I will move to the next slide. Let me repeat this because I will not. 1b minus c, because was minus 1, because this was 1, -1, and that's the denominator. Okay, so what we have? Let's maybe rewrite a few things. This one is easy to integrate, we know that. And actually, for this quadratic irreducible factor, we have to be careful because we can see what we have in the denominator, x squared plus 4. I know that everybody thinks about inverse tangent, arctangent. But arctangent, we may apply if only constant is on the top. We still have that x. That means I will split this integral for the x over x squared plus 4, and then minus 1 over x squared plus 4, because I can split the numerator and keeping the same denominator. Okay, I mean the first integral 1 over x is just natural log of absolute value of x. Excellent. And the middle part, we will probably do the u substitution. Yes, we can see that it will work, which we will do in a minute. But this one, we have 1 over x squared plus 4. If this will be plus 1, it's just arctangent of x. But that 4 is affecting inverse tangent of x over 2 and 1/2. And I will add the constant of integration. Yeah, because we remember that 4 affects the answer this way, x over 2, 1 over 2. Okay, but the middle part, I will let u to be x squared plus 4, because we can see the inverse tangent will be not involved because of the extra function on the top. Du is 2x dx, and I have x dx. Let me actually write this integral. Okay, x squared plus 4 dx. And we can see x dx is part of the integrand, then I will just divide everything by 2. X dx will be 1/2 du. Okay, I can maybe write this. That means x dx is 1/2 du, and denominator was u. Now it's easy to integrate because this will be just 1/2. Integral of 1 over u is just ln of u. But we have to substitute. We will substitute back, instead of u, we will put x squared plus 4. Okay, and I can copy that integral. Okay, and actually I need my first term. Oh, let me do this. It will take just a few seconds because I like the nice, that means this will be natural log of x. That means this is the final answer. But the part for the u substitution, I will rewrite here. X squared plus 4, du is 2x dx. Yeah, we can practice again. 1/2 du is x dx. That's what we use. Okay. That means please remember, it's a little bit different integration, which we know this integration when we have this quadratic irreducible. Let's solve one more problem, and then you will practice. Oh, I do have answer typed. Okay. Integrate the integral from integral of rational function x squared minus x over x minus 3 times x squared plus 1. Definitely this is proper rational function because denominator, the polynomial from the denominator has a greater degree, 3, and the top is squared. And we even have the product form. Excellent. I mean, we're expecting two partial fractions. X minus 3, the linear one, great, but this one is x squared plus 1, quadratic one. I will put a, and again, bx plus c. And let's find coefficients a, b, c first.